distribution. And it's going to get a special name here. Let me get, where's my pencil? Let's pick a good color for this. Let's go bright purple. No, sky blue. And it's going to be the binomial distribution. And this is probably one of the most useful distributions due to binomial, right? By 2. And it's a limited probability, and what ends up happening is that the experiment gets repeated. For a limited number of results, or a limited fixed number of trials. Yeah, I'll use the book's word fixed. A fixed number of trials. There are only 2 outcomes. The experiment off camera, I fought with Blackboard, so I'm kind of in grumpy mode right here, but I will get in cheery mode. The experiment has 2 results. Success or failure. And we will denote the probability of success as P of S is the same for each trial. Which also means that the probability of failure is 1 minus the probability of S. Right? Because if you only have 2 outcomes, they have to add up to 100%. And 1 minus the probability of the success will give you the probability of failure. We think about the sample space, and we can say that's the probability of success, and that's the probability of failure. They have to add up to the total. And X counts your successes. And so that's what we base the binomial probability distribution off of. So when we'll turn this into some variables that we can use when talking about it. We'll say that N is the number of trials. P is the probability of success. On one trial. Any individual trial, the probability of success. Q is the probability of failure. For one trial. And we should note that it is 1 minus P. And X is the random variable that counts the successes. And so let's look at a binomial experiment and what we can do with it. So I think if I go through here, well, let's put the probability into a calculation, and then we will go from there. So the probability of a given number of successes is going to be the number of combinations that many successes can have. So I have my total number of trials, and I get the combinations of how many are successful, times the probability of success to the power of X. Because remember, probabilities multiply when we have ORs, or ANDs, sorry. And then in the probability of success, or failure, notice these two exponents. If I add them together, it gives me the total number of trials. And if I expand out my combinations, I get this. Now we're going to have many tools to calculate this. Because this is such a used probability distribution. But let's look at some of these and then look at the tools that we have. So, rotator cuff surgery has a 90% chance of success. So, it has a probability of being successful of 0.9. That means its probability of being unsuccessful is 0.1. If we perform the surgery on 3 patients, we can find the probability of it being successful on exactly 2 people. Right? Now, there are some caveats here. We have to assume that each surgery is independent. We're not lining up the same doctor performing the same surgery over and over again. There would be some dependency on the probabilities, and it wouldn't be the same unless there was enough time in between it that each surgery could be considered fresh. So let's use this formula here to calculate this probability, capital P of 2. And so it's going to be 3 combined with 2 times 0.9 to the second power times 0.1 to the first power. And if I break this out, I get 3 factorial over 3 minus 2 factorial, 2 factorial. So 3 minus 2 is 1, and 2 factorial, this will just, let me rewrite the rest of the formula here. And so this is 3 times 2 times 1 over 2 times 1, so the 2 and 1 will cancel, so I'll have 3 upstairs. And then 3 minus 2 is 1, and 1 factorial is 1. So that gives me a 3 out front. And then that's a positive 9, sorry, that's, don't know, probably dragged my pen across there. There we go. And so I have 0.9 squared, which is 0.81, and then 0.1 to the first is 0.1. And if I multiply these, I get 0.81, I get 3, 2.41 with 3 decimal places, or sorry, 2.43, but I have 3 decimal places, 243. So I'm doing some mathematics in my head. Your calculator can verify it. And so that's a binomial probability for one outcome. But the actual distribution would have multiple outcomes, right? Remember, our distribution would be all the possible outcomes for this. And so that would be, what are the possible? There's 0 successful surgeries, 1 successful, 2 successful, or 3. And so we have some probability for each of these. Now let's look at what our technology can do for us here and help us a little bit more. We'll come over here and we'll use the binomial distribution. And so what I want to do here is I'm going to make my x values 0, 1, 2, 3, and then this is going to be my probability of x. What I'm going to do is I'm going to equal binomial distribution. So the first thing I need is x. So in this case, x is 0. But I'm actually going to put the cell it's coming from. It's coming from B2. Then in the number of trials, and we had 3 trials. And then in the probability of success, which was 0.9. And then we're going to later see that we can do accumulated probability, but for right now, that's not true, so we're just going to type in false. And we get the probability. And if I drag this down, it gives me the probability for each particular outcome. Notice the 0.243. And so the binomial distribution lets us calculate this. In fact, I'm going to